Hi! The next portion of our class is going to be about using radioactive isotopes to date materials. And in order to do this, it helps to have a strong basic understanding of why radioactivity exists in the first place. So let's start off with a very basic question, which is why do some nuclei decay and others don't? Atoms contain both positively and negatively charged particles. The negatively charged particles, the electrons, are spread throughout most of the volume of the atom. But the positively charged particles, the protons, are squished down into a very small area in the center that we call the nucleus. And so now let's think about what it means to have a whole bunch of positively charged things in one area. So you can think back to those days when you were a kid, when you used to play with magnets, and you know that if you put two bar magnets together in one direction, where you have a north pole and south pole together, they attract. If you put two north poles together, then they repel, right? So again, when we're talking about positively charged particles like protons, it's the same electromagnetic force that governs their interactions. And so you have two particles with similar charges. You try and put them together, and their natural inclination, based on the electromagnetic force, is to just scooch apart from each other. They're going to repel each other. So why doesn't that happen? We don't see nuclei completely flying apart. We see them kind of like dribbling off little bits if they're super large, but we don't see all nuclei, just all of the protons going flying out most of the time. Well, there's two reasons that this does not happen. The first is that most nuclei don't just have protons in them, they also have neutrons. Now, neutrons have no charge, and in effect, what they're doing is they're acting as spacers so that those positively charged particles are not all squished up right next to each other. So if you ever took physics and you studied electricity and magnetism, you might remember something called Coulomb's law. And this is a slightly dumbed down version of Coulomb's law, but it's the force between two charged particles is proportional to the magnitudes of the two charges, that's Q1 and Q2, divided by r squared. And r is the distance between the charged particles. So basically, the smaller that distance between the two particles, the stronger the force is going to be. And so by increasing the distance between the particles, in this case with neutrons, the repulsive force between the protons is somewhat mitigated. So that's part one. Okay, so the repulsive force between the protons is mitigated, but they're still going to repel each other, just not as strongly. So what else is going on here? Well, there's this other force that we call the strong nuclear force that holds things together within a nucleus. So part of it is holding quarks together into what we call protons, neutrons, and electrons. So holding teeny tiny building blocks into slightly larger but still tiny building blocks. But the other thing that the strong nuclear force does is it actually holds the protons and neutrons together. But there is a drawback to the strong nuclear force. It's not infinitely powerful, despite the fact that it's the strong nuclear force. It only operates over a limited distance. So kind of like Coulomb's law, it falls off as the particles get further and further apart, but it decreases more rapidly with distance than the electromagnetic force does. So what I've been showing you here is this small nucleus, which is helium-4, actually. It's 2 protons and 2 neutrons. But now imagine that strong nuclear force. When you have more than 2 protons, you have more than 2 neutrons, you have a whole bunch of protons and neutrons all together. Once again, you have the strong nuclear force holding those protons and neutrons together into a nucleus, and it's still operating over a limited distance. So, ignoring the numbers of protons and neutrons, you can actually see in my very low-tech PowerPoint drawing, imagine that you keep throwing protons and neutrons on. There's a limit to how closely you can squeeze them together. At some point, you're going to have so many protons and so many neutrons that you just can't hold them together. You can hold some of them together, but not all. And what happens when your nucleus is too big to really hold together is that little bits of it start to break off. Not the entirety of the nucleus, but small pieces. So we see this phenomenon of nuclei breaking up. We see this happening under very specific conditions. We see it happening when there's so many protons and neutrons that no matter what the makeup of that nucleus is in terms of protons and neutrons, the strong nuclear force just can't hold everything together. So we see that happening. We see it when there's too many protons and not enough neutrons to keep them spaced. And we also see it when there's too many neutrons compared to the number of protons. A couple of weeks ago, we talked about the chart of the nuclides, or the table of the nuclides, and you remember that the x-axis here is the number of neutrons and the y-axis is the number of protons, and so there's this very narrow band where we see things actually existing. The black isotopes here are the ones that have the optimum number of protons and neutrons to stay together. And then it's possible to put things together and keep them together for a little while if you move out from those nice stable configurations. And then past that, you just can't even keep them together at all. So that's sort of what we see for the chart of the nuclides. All right, so just a couple of vocabulary terms that you'll hear me referring to throughout the next few videos. The first is what we call a parent isotope. And so what's going to happen as we undergo these radioactive decays is that we're basically going to be turning one element into another. This is kind of like the old alchemists, right? So the element that we start with, the isotope of the starting element that we are looking at, is going to be called the parent isotope. So that's whatever we're looking at before radioactive decay happens. And then I don't know why they had to be gender specific here. It's not the child isotope, but the daughter isotope is what's produced by radioactive decay. So whatever element you're left with, whatever isotope of that element that's left after radioactive decay, that's the daughter isotope. Sometimes you'll see it referred to as the radiogenic daughter or the daughter product. All of those things are used in literature, but if you just remember that the parent is what you start with and the daughter is what you end with, then all the little permutations of parent what and daughter what will be pretty clear. So now what we're going to look at is we're going to look at some trends. So hopefully you remember how to balance a nuclear equation, because what I'm going to do is I'm going to quick go through and I'm going to show you 3 different types of commonly occurring radioactive decay. And all of these I talk about in my video on balancing nuclear equations. So if you need a quick review, I'll drop a link in the description. Here, we're going to start out by talking about beta decay. Okay, what daughter isotope is produced by beta decay of magnesium-28? So when you're doing one of these things, the first thing you're going to do is write the isotope that you're starting with, the parent isotope, which in this case is magnesium-28. And it would be very useful to know what the atomic number of magnesium is, so you can look at your periodic table. Magnesium is element number 12. So now we have 2812 magnesium, and it's going to undergo beta decay. So we know what a beta particle is. It's written this way: 0 mass number, -1 atomic number. And then we just have to figure out what else is left behind after we undergo beta decay, which basically means the nucleus shoots out a beta particle, an electron. What is left behind when that happens? And so you're going to balance the mass numbers. 0 plus what equals 28, 28. -1 plus what equals 12, 13. Okay, and what's element 13? Here's what we've got. Aluminum 28. Okay, now that is the daughter isotope when magnesium 28 decays, aluminum 28. And now let's look at the location of those two on the chart of the nuclides. So here we have magnesium 28, and here we have aluminum 28. So notice the direction that we move on the chart of the nuclides as we go from our parent isotope to our daughter isotope as we undergo beta decay. So we're moving basically up and to the left. Now let's look at another beta decay. What daughter isotope is produced by beta decay of 143 praseodymium? There's an element we don't use a lot in our everyday lives. Well, you can look at your periodic table, and I will look at mine real quick. Praseodymium is element number 59. So here's praseodymium 143. And again, it's undergoing beta decay, so it's going to produce a beta particle as 0, -1 beta. And now we do our math, and you can check my math, pause the video if you want to, but I come up with 14360. Element 60 is neodymium. I think that's how you pronounce that. And now we've popped back to the table of nuclides, or chart of the nuclides. Okay, here's praseodymium 143. And we made neodymium 143, which is up here. And once again, you can see we're moving upward and to the left. And what you'll find, you can go through any number of beta decays and look at both the parent and the daughter on the chart of the nuclides, and what you end up finding is that you're always moving up and to the left. What daughter isotope is produced when you have alpha decay of astatine 212? Astatine is element 85. I just pulled that off my periodic table. And we're going to undergo alpha decay, which means an alpha particle is popping off of the nucleus. What's an alpha particle? It's basically a helium-4 nucleus. So it's 4-2 alpha. Sometimes people write 4-2 helium. That's also okay. And now, do the math. What plus 4 equals 212? Well, that's going to be 208. What plus 2 equals 85? Well, that's going to be 83. So what's element 83? It is bismuth. So we're making bismuth 208 as our daughter product. Let's go back to the chart of the nuclides. Here's astatine 212 right here. Here's bismuth 208. So you can see which way did we go. We went down and to the left, and we didn't just go down one square, we actually went down 2. And now let's look at another alpha decay and see if that pattern holds. What's our daughter isotope going to be if we have 225 actinium decaying by alpha decay? So actinium is element 89, and again, we're going to pop off a 4-2 alpha particle. So do the math. And what we end up with is element 87, which is francium. And so here's our product, francium 221. Back to chart of the nuclides. So here's actinium 225 right here. And you can see francium 221 is down here. And so once again, we've gone 1, 2, down and to the left. So you can see that these decays follow a very specific pattern on the chart of the nuclides. And I'm explaining this to you so that if I just say, here's this isotope, it decays by alpha decay, you can then look at chart of the nuclides and actually figure out what it is without having to go through the math of balancing the nuclear equation. Okay, one more thing that we see a lot of, and that's positron decay. A positron, remember, is something that's like an electron but positively charged. And so here we're looking at gold 194, and gold is element 79. So let's pop off a positron. Now, a positron has 0 mass number, just like an electron, but it has a +1 atomic number. So there's our 0, 1 positron. And we can do the math, and we come up with element 78, platinum, and we're dealing with platinum 194. So you know the drill, back to the chart of the nuclides. So here's gold 194 right here. Here's platinum 194 right here. So now we're going down and we're going to the right. Okay. And I'm just going to do one of the positrons. So I'm just going to tell you straight out that the positrons always follow this pattern, just like the beta particles and the alpha particles. So remember here we've got beta decay, sometimes called beta emission, where you're popping off a beta particle or electron out of your nucleus, where you're going up and to the left on your chart of the nuclides. And then you have positron emission, where you're going down and to the right. And remember, positrons turn protons into neutrons. So then you have more neutrons, fewer protons, and that increases your neutron to proton ratio. And finally, you have alpha emission, and that's a really good way to quickly decrease the size of your nucleus. So let's go back to the chart of the nuclides, and let's look at what sort of isotopes undergo which sort of radioactive processes. Because once you understand the movement within the chart of the nuclides, you will also understand why things decay the way that they do. So, very generally speaking, if you look at this chart of the nuclides, you see this band of black that we've talked about before that we call the band of stability, and any isotope that is not stable really wants to end up as a stable isotope. And when I say wants to, I know I'm anthropomorphizing, but really what that means is just very simply, it's more energetically favorable. Okay, so you can think about that from a thermodynamic point of view. That is a low energy configuration. So the isotope will decay in whatever way it can to get to that band of stability. And it will do it generally in the most efficient way to get there. So not everything can decay and become stable with just one radioactive decay. Sometimes you'll need 2 or 3 decays, and it's not going to go, away from the band of stability and then back to the band of stability. That's not what it does. That is actually not energetically favorable. So it's always going to follow the most thermodynamically favorable approach to get to the lowest energy thing. And so basically it's just going to find the shortcut to get to the band of stability, however that happens. Okay, so if you look at this band of stability running diagonally, then there's things that are kind of below and to the right, where my mouse is right now. And there's things that are above and to the left, where my mouse is right now. So if you're below and to the right here, what you want to do is you want to get up to the band of stability. And the way that you do that, there's only one of those processes we looked at earlier that goes up, and that's beta decay. So everything that's down here, down below the band of stability, is going to end up undergoing beta decay to get back towards the band of stability. Now let's talk about the stuff that is up on top of the band of stability, and that's going to want to go downwards. Now we saw two downward trends in our summary. One goes down and to the right, and the other goes down and to the left. So back at our chart of the nuclides, if we're up here, going down and to the left, as you would if you were doing an alpha decay, that's just going to run you parallel to the band of stability. It's not really going to help all that much, right? What you need is you need a positron decay that's going to take you down and to the right. That will get you to the band of stability. So everything on this side of the band of stability is going to undergo positron decay. Well, then why do we need alpha decay? One brings you one way into the band of stability, the other brings you the other way. Where does the alpha decay show up? Well, the answer is it's a good way to make nuclei smaller. So remember, once you get above element 83, bismuth, there are no stable elements. And so what you can see is that if you're up here, or even up here, you're going to have to somehow pull yourself way down to the point where you can even get close to the band of stability. And that's where we see a lot of alpha decays going on, is in this area. Now, if you start up here, you're never going to just alpha decay, because you can go alpha, 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 and you can see that we're not going to hit that band of stability. You're also going to need to pull up with beta decay. So it's going to be a mix of alphas and betas. But in general, you can look at the chart of the nuclides, pick any isotope on there that is radioactive, and you can predict how it will decay. And the way it will decay is through the process that takes it closest to the band of stability, which may be a process that involves one radioactive decay, or in the case of some of the very heavy elements, it may be a whole chain of different radioactive decays that is predictable. So that is the basic idea behind why radioactive isotopes decay and why they decay the way they do. And so take a look at the worksheet, see what you can do in terms of predicting how things will decay, and then go on and watch the next video, which is about the kinetics of radioactive decay, because that's also really important when it comes to isotope dating.